Welcome. Today we're going to be taking a look at the notes worksheet entitled Trigonometric Equations Conditional Day 3. And so this lesson offers us an opportunity to reinforce and review some of the objectives that we saw on the last lesson. So we're going to go ahead and take a look at a couple things here today, just solve a few more equations and see if we can solidify some of those skills from the last couple days. So it looks like at the top here, just to review what we talked about, really a three-step process. So it just says, what are the 3 steps to solve trigonometric equations using approximations? And let's see if we can kind of do this without you looking back a little bit. See if you remember what we did first, and then what we did second, and then what we did third. And then, of course, I'll write my answers in here, and then we'll do exactly that. I'll try to be as clear as possible in terms of this laying out the 3 steps. So here we go. Number 1, of course, here, let's see, we have to find the reference angle. So what we decided is take the inverse of, and I wrote it like this on the previous notes worksheet. So what we want to do is take the inverse of the absolute value of the ratio to get the reference angle. And remember that reference angle, that x prime, is always acute and always positive. So by taking the absolute value, making the ratio positive, and then taking its inverse, you're guaranteed to always get from the calculator what would be considered the reference angle. So that's what we did yesterday. That was the key first step. Seems a little odd when we maybe are trying to get a negative ratio, but at least at the beginning, what we want to do is get the reference angle. So just treat it as positive temporarily. Okay, now let's go back and think about the equation. And what we want to do is determine the quadrants for our solutions. So obviously our job is to solve for the variable there. So we want to know what quadrants they're in. So find the quadrants that x will be in. So that's knowing that sign chart, of course, where sine and cosine specifically are positive and negative. So find the quadrants that x will be in. And then number 3 is set up an equation. Well, really 2 equations. Let me modify that quickly. Typically, that's how it's going to work, as we probably will have 2 quadrants there. So set up 2 equations using the quadrant rules, of course. And we laid out the quadrant rules on the previous notes worksheet. So set up 2 equations using the quadrant rules to solve for the variable. And that, everybody, is pretty much it. If you remember on yesterday's notes worksheet, I kind of put a little 1 and a 2 and a 3 by each of our steps just to be very clear as to what I was trying to do, because this can be a tough process to go through. But I think if you follow it accordingly, should have some pretty good success. Remember, everyone, really, unless we're at the maximum or minimum of our cycle, we are going to get 2 solutions per cycle. And so as a result, we kind of need to use these steps in order to pull that off. So let's give it a try. I believe I have 3 examples that will allow us to reinforce some of these ideas. So here we go. It looks like a simple harmonic motion problem here. A weight suspended from a spring is vibrating vertically according to this equation right here. Interestingly enough, it looks like we also have a little phase shift in there, but that's fine. D is going to be the distance of the weight from its rest position. Up is positive and down is negative. Let's see, find the 2 smallest positive values of t for which the displacement of the weight above its rest position is 4 centimeters. Okay, sounds great. So it looks like given the output, can you go ahead and find the inputs? Now remember, theoretically, there are an infinite number of inputs. In this case, we're going to go with the first 2, sort of the 2 in the primary cycle. So let's give it a try here. Everyone, if you would, let's go ahead and put 4 in for D. Kind of start it out here. So 3 pi over 4t, and then minus that pi over 4. We'll kind of have to deal with those pieces a little later on. But let's start out with just good old-fashioned algebra here. Obviously, our goal is to solve for the variable. what makes these unique is the process in order to pull that off. But I guess I would argue everybody's going to divide by 10 first. So let's divide by 10. So 0.4 instead of 4. And then sine 3 pi over 4 t minus pi over 4. Okay, now everybody, if you would, what we need to do is come up with the reference angle. So I'm going to put a little 1 right here, just in terms of this is going to be the first step in that 3-step process, of course. And we need to get t prime, essentially, the reference angle that will allow us to kind of move forward and get our two values. So in this particular case, what I'm going to do is the inverse sine of 0.4, which should give us our t prime. So again, always make sure that this value is positive in order to pull this off. Otherwise, we have to do a whole lot of interpreting. I mean, we can do it. I just feel like this is a little more straightforward in that if we take the inverse sine, and it's positive anyway, so that's not a big deal, but basically if I go ahead and take the inverse sine of 0.4, that will give me my, my t prime here. Okay, well, let's go ahead. I'm going to bring my calculator up, and let's get that piece going. Everyone, just make sure, radian mode, please. And let's go for it, everyone. Type in inverse sine 0.4, and that looks good. To about 4 decimal places there, I got 0.4115. So t prime is 0.4115. All right, step 1 completed. That looks great. Now, step 2 is to really focus in on this piece right here. So what we're asking ourselves is where are we going to get a sine ratio of 0.4? And of course, it's positive, so where do I get positive sine ratios? So now, everybody, I go to my step 2 here, and I need to figure out the 2 spots in my cycle where this is going to occur. And I guess the argument can be made that we're going to get 1 in quadrant 1 and 1 in quadrant 2. So sine is positive in quadrants 1 and 2. So I just lay it out like this, and then step 3 will kind of go right with this momentarily. So the idea is here we're going to undo the sine by taking the inverse and set that equal to our angles in those quadrants. When I undo sine, everybody, unlike what we saw yesterday, I have a whole lot more left than just t. So it was nice yesterday. We just had a t equals and our quadrant rules, and we were ready to go. Now, everybody, I undo sine, and I still have some stuff I need to deal with. So here's what we do. When we undo the sine, we get this piece right here. Now that's equal to the quadrant 1 angle, and it's also equal to the quadrant 2 angle. So I'm going to set those up simultaneously here, and then we'll throw in what the quadrant 1 angle would be and what the quadrant 2 angle would be. Okay, so again, I undo sine, and when I undo sine, we get our split with what's left. This is equal to the quadrant 1 angle, and you're going to have to know these quadrant rules. I'm afraid there's not too much wiggle room here, but if you remember in quadrant 1, the good news is our reference angle is the angle. So in quadrant 1, the angle that has the sine ratio of 0.4 is this angle right here. That's the one in quadrant 1. If I did sine of this, it would give me this. Inverse sine of this gave me that. Okay, and then we're going to solve that. We're going to add this. I'm going to inherently divide by this. That's going to give me t. All right, now let's come over to the quadrant 2 piece, everybody. And whatever was left after I undid sine is equal also to the quadrant 2 angle that has this sine ratio. Well, how do I get that quadrant 2 angle that has that sine ratio? Unfortunately, again, there are calculation limitations here. It's unable to give it to us, so we have to find it indirectly. And in this case, what we want to do, as we saw yesterday, is just pi minus. And so that would be it right here. This is the angle. That's what's intriguing about this, everyone. This is the angle that has a sine ratio of 0.4, and that's what I was looking at. 2 angles that have a sine ratio of 0.4, this one in quadrant 1, this one in quadrant 2. So I do my split when I undo sine, and now I solve. Well, everyone, I guess here's what I would ask. I don't have the step-by-step here, but I'm assuming everybody can kind of pull this piece off. So everyone, if you would, add pi over 4 to both sides. and then you're going to get something right here. And then if you want to treat this as a decimal and then go ahead and divide by it, that's perfectly fine. I've seen in the past students will do something like this. They'll multiply by the 4, and then they'll divide by 3 pi. Just remember, if you divide by 3 pi, you do need parentheses on that piece. Well, I'm going to do a little leap of faith here so we can kind of get this moving to the next piece. I'm going to write my two answers down. After doing this, if for whatever reason you're not able to kind of pull that off, please put a little question mark by it, and I'll be happy to take a look at it with you. But add pi over 4 to this, and then divide by this thing right here, whatever that may be. Somehow eliminate that piece. Anyway, I get just over half a second. And then over here, same thing. This, everybody, is just a number. So take this, add pi over 4, and then divide by this piece right here. Again, just seeing if you can pull this off rather than me walking through those steps with you. But essentially, I would get this as well. And those are going to be your two values. Okay, so let's see, actually. I never put a 3, just want to make sure everything is highlighted for you. There's my step 3. So now I set my equations, whatever's left, to the two angles. In this case, one in quadrant 1 and one in quadrant 2. So I guess I have a couple blanks over here. I might as well just go ahead and put those in. So one right here, and then one right here. Excellent. All right. Good. Let's go ahead and try something else. Example 2, everyone. It says, given some information of a sinusoidal model, nice little review here. Let's see if we can create a sinusoidal model based on these characteristics, and then actually go ahead and solve. So let's see. If you remember, the amplitude really referred to the A value. Period, it's going to refer to the B value. Midline is going to refer to the D value. We're starting at a minimum, so is that going to be sine or cosine? So good little review from some previous information that we've gone over. So let's talk about this. I guess the first order of business is to realize if we're starting at a minimum, we refer to this as sort of a flipped cosine. Just FYI there. So it'd be great actually if you can pause the video for a second and see if you can come up with an equation, y in terms of x, meeting that piece. No phase shift necessary here. And so I would ask you to go ahead and pull that off. Given an amplitude of 4, period of 15, midline of -3, and I think I kind of gave it away that it is going to be a flipped cosine. Why don't you see if you can pull that off? All right, well, let's see how you did. When I wrote mine, realizing it was a flipped cosine, so I did a -4 out in front, and then cosine, of course. And then remember, it's 2 pi over the period, everybody. So 2 pi over the 15 times x. And then how about a -3 on the back? Again, no phase shift here. All right. So I think that should meet all the criteria in this particular case. Now, you know, the way we've been working with models before, given an input, so given an x, you would be able to tell me the corresponding y. Now, here's where we're at, trying to find if I give you a y, can you somehow represent at least 2 primary x's? And then could you maybe extrapolate further to the infinite number of x's? So for some of these y values, if I give you one here, there are an infinite number of x's here. So again, the trig equations are unique in some respects. Okay, so let's see. It says from 0 to 15. And by the way, I'm just going to put this here, not that it's necessary. But this would be our primary rotation around, starting at the y-intercept. And remember, the period is 15 units. And by the way, keep that in the back of your mind if you would. So the period's 15, not just 2 pi like what we've seen before. So from 0 to 15, find the x-intercepts. Okay, sounds good. I think we can pull this off. So first and foremost, we have to decide, and we're going to do this algebraically, by the way, find those x-intercepts. Well, what do we know about any x-intercept for any function? Well, of course, we know that the y value is 0, sometimes called, of course, and we've seen this before, the zeros of the function. And so in this case, we're going to find the real zeros by solving for the x-intercepts here. So let's just make sure I've got mine all laid out properly there. There we go. And that's the idea. Given the output, Can you find the corresponding inputs? Okay, well, again, let's let just at least some of the good algebra take over for a moment or two. Everybody add 3. Let's bring it on over. So I have this piece right here. Now, we've seen this a few times now, so hopefully we're going to get into a little more of a rhythm with this. Obviously, this is not easy by any stretch of the imagination, but what we want to do is start to develop just a routine with it. So divide by the 4 there. And that's where I'm at this point. Now comes the tricky step, and that is basically undoing the cosine. Unfortunately, it's not quite as easy as just doing an inverse and then moving on, because when we do the inverse, it's only able to give us one value. At best, it's going to be one of our answers, but it's never able to give us the other, of course, and so we have to interpret and then kind of figure out where to go from there. Well, anyway, let's go for it. I'm going to do my little 1, 2, 3. I might be running out of room a little bit here, so I'll go across the board if need be. Anyway, here's what I'm thinking. We want the inverse cosine. Now, this is what I do, everybody. I do the inverse cosine of just 3/4 in order to get the reference angle. So that's just how I pull it off. My first order of business is to get a reference angle, and I know it is always acute and always positive. By doing an inverse on a positive ratio, you're guaranteed to get this piece right here. So I'm going to go ahead and bring my calculator up one more time here. And let's do inverse cosine 3/4. And I get that right there, about 0.7227. So there, everybody, is the x prime, 0.7227. Excellent. Now I'm going to come right over here, everybody, just on this side. And so once I get my reference angle, now I have to go back and really focus on this piece. So everyone, if you would, focus just on this idea right here. In fact, I think I did this yesterday. I kind of boxed that up like, all right, here we are. Now's where the trig comes into play. And so I guess what I would say to us is, all right, remember, we're undoing cosine, which means what we're trying to really do is find the angles, plural, that have a cosine ratio of -3/4. Okay, well, where is cosine going to be negative? Let's just start in general terms there. Cosine is negative, everybody, in quadrant 2 and in quadrant 3. So that's what I do. I kind of lay out my quadrants right there. And then right below it, now I set up my rules. I undo the cosine, so cosine disappears, and then I'm left with this, everybody, 2 pi over 15x. So when I undo the cosine, that's the only thing that's remaining, that constant next to my variable. And whatever is remaining is equal to the two angles where cosine is -3/4. So what we have to do is now say, okay, well, the angle in quadrant 2 with that ratio is pi minus the reference angle. And then I'm just going to have to come over here, everybody. But in quadrant 3, same thing, everybody. Basically, whatever's left over is equal to the quadrant 3 angle. That has a cosine ratio of -3/4. I undid this in order to get the two angles. The quadrant 2 angle is pi minus, and the quadrant 3 angle, everybody, is pi plus. And now it's an equation we can deal with. It's something that I can just, not really ... but essentially that's going to be it. This divided by this. And that should get us our couple answers here. So we're going to go ahead and get that taken care of momentarily. Just want everyone to kind of stare at the screen there for a sec and make sure it's really starting to click for you a little bit. But that's looking pretty good. I'm just trying to see what I have on my paper. It looks like I have the same thing, so just sort of a solution from here. So here's what I'd ask you to do. See if you can pull this off. Take pi minus this. That's a number. And then maybe multiply it by 15 and divide by 2 pi. But just remember, of course, when you divide by 2 pi, that has to be in parentheses. Well, let's see. I get an answer of, it looks like about 5.7747. And then over here, I do the same thing. This divided by this in some way, shape, or form, everybody, and I get about 9.2253. Now remember the nature of symmetry as we're working around here. If I were to take these two values essentially and add them together, take a look at what they get. Again, not really a coincidence there. So we can start to find some ways potentially to shortcut a couple ideas. But really, I would ask you to make sure you're really solving things correctly. Okay, so regardless, everyone, here's what I have. 7747 and then about 9.2253. So in our sinusoidal function, and I'm going to just go ahead and graph this and just kind of thinking about it for a sec here. I'm going to go ahead and type that in and maybe tweak my window a little bit. So it was -4 cosine, and you guys can just watch for a sec here. That would be great. Take a breather for a moment from jotting things down. I don't mind doing the work up here for a sec. And let's see, I'm going to hit my window on this. I'm going to go 0 to 15. So that's what we kind of decided there. And let's see, amplitude is 4, midline is down at -3. I'm going to buffer this a little bit. I'll go from -10. Let's see, up to 5 should be fine. And let's see if this is legitimate. There we go, not too bad. So there's my sinusoidal wave, and I've got this piece right here starting at the min, up, down, and take a look, everyone. 1 x-intercept here, 1 x-intercept there. And if we were to count it out, we should get the 5.7 and change and the 9.2 and change right there. Now remember, of course, everyone, here's the idea, of course, that is going on again and again and again. So these two intercepts are going to keep repeating over and over and over. The question is, after how many units do they repeat? So that brings us obviously to the next question. Now here's where we want to just be a little careful, and I need to clarify what we did last time around. I guess this was from day one. It says represent all of the x-intercepts. Okay. Well, let's kind of talk about this. I had one at the 5.7747. We could call it our primary x-intercept for lack of a better description. And the question is, how long will it take before I get my next x-intercept, my next x-intercept, et cetera, et cetera? Well, if you remember day one, what we would do is just put a little 2 pi k on the back and move on, because the basic sinusoidal function repeats every 2 pi. But of course, that's not the case right here. Our values aren't repeating every 2 pi. This is a more comprehensive sinusoidal model. In this case, everybody, our values are repeating every 15 units. So instead of a 2 pi k, and this is here what I need you to write in, they're going to repeat every 15. And so it's going to be a plus 15k. So by the way, and I'm not going to track it out on the calculator, but basically we would see another x-intercept, if I add 15 to this, at about 20.7747. And then another one at about 35.7747. So every 15 units before and after this value, we would see another x-intercept. So this, guys, it's not just 2 pi k, it's the period. And so I don't know, I'm just going to write that in here, just kind of thinking about it. Just make sure that it makes good logical sense. Okay, so the next one then, I would write as 9.2253 plus 15k. Good. All right, so an infinite number of solutions to that equation, and this would be the mathematical representation of that. Well, let's try one more. So let's see, a Ferris wheel has a diameter of 100 feet. A person riding the Ferris wheel gets on at its low point of 5 feet above the ground. It takes 2 minutes or 120 seconds, and we'll just decide which one we want to use here for each revolution. Write a sinusoidal model for a person's height in terms of time. Okay, sounds good. So I don't know, I'm very visual, so it just helps me to do a couple things here. So diameter is 100 feet. I'm just kind of seeing that, and it looks like she's getting on, let's see, 5 feet above the ground, so from there to there is 5 feet. That's not great, but you'll get the idea. So 5 feet above the ground. And so in terms of graphing this, again, just always helpful for me, it looks like getting on 5 feet above the ground and then all the way up to 105 feet above ground. So that's what I'm seeing right there. And then in terms of the period, I'm going to go with the 120 if you decide to go with the 2 minutes there, which actually might be a touch easier, but I'm going to stick with the seconds here. So something like that would do. And then basically here would be the sinusoidal wave, something like this, up and back down. Okay. Well, let's see if we can write a model here. In fact, again, since I've done some of the information here for you, especially have represented it visually, it would be great to see if you could go ahead and write a function for this. Remember, you'll need a midline, you'll need an amplitude, and then I think you could let it roll. So pause for a minute if you get an opportunity, and then come on back and let's see. All right, well, let's take a peek here. When I did this one, I have a midline of 55. Seems like that's right in the middle there. And as a result, it looks like the amplitude would be 50. So just kind of thinking out loud with this, 55 is the midline. The A value would be, in this case, we're starting at the bottom. So A is going to be negative 50, and then cosine. B is going to be 2 pi over 120, et cetera there. Okay, so I think we have enough. That's sort of what I came up with, just kind of thinking out loud with it. And I have h in terms of t. If you want to do y in terms of x, of course that's fine. But I'm seeing this model as a negative 50 cosine, 2 pi over 120. I would go as pi over 60. So pi over 60x, and then plus the 55. All right, so everyone take a look at that piece. Make sure there is some agreement on that. Again, just kind of thinking of what I see here and putting this together. All right. Well, again, when we've worked with this before, I would give you an x, you would come up with a y, or I would give you a y, and you would only come up with one x. And you would just do a straight up inverse without any interpreting, excuse me. So in this case, we're going to take it a little further here. So when will the rider be 80 feet above the ground? I'm just going to go back for 1 second. And of course, as we know, as this person moves around in circular motion, it's going to hit 80 feet over here and 80 feet over here, once on the way up and then once on the way down. So 2 solutions in our cycle as opposed to just the one. Okay, well, let's go for it. So last time around, guys, by now maybe we're firing on all cylinders. So let's see, negative 50 cosine pi over 60 times x, and then plus 55. All right, let's go for it. First and foremost, bring over the 55, everybody. And if I bring over that 55, I get 25 equals negative 50 cosine pi over 60x. All right, step 1 completed. Everybody, divide by the negative 50 there. And this is interesting, as we get a negative 1/2 cosine pi over 60x. Okay, now, what makes this intriguing to me is the fact that we actually know the angles that have this cosine ratio right here. So if I asked you where do we have a cosine ratio of negative 1/2, you probably could do more than just tell me the quadrants that would occur. You could actually probably tell me the angles right away, and then we can get moving on this. I'm going to avoid that for just a second. I will come back to that very piece, but I do need to lay out one more time at least sort of the step-by-step process. So I see this 1/2, and it just sort of piques my interest. But for right now, I'm going to ignore that fact and just go with what we've been doing, just using the calculator to get an inverse and then going from there. So I'm going to do exactly that piece. So everyone, if you would, what we need to do is find out where we're going to get a cosine ratio of negative 1/2. The first order of business, of course, is to find the reference angle by just taking the inverse cosine of 1/2 and getting our x prime. So that's step 1. I'm going to do that up here. And so let me come on back. Inverse cosine of 1/2. And so I've got about 1.0472. So that would be my first step, just thinking about that piece, 1.0472. All right, very good. Now, again, go back to the equation, of course, and remember what it was asking. In order to undo cosine, I need to find out the angles that have a cosine ratio of negative 1/2. And find out where they're located. So the quadrants where we would get a cosine ratio of -1/2 would be in quadrants 2 and 3. Okay, perfect. Now I do my step 3 based on that, and I basically say, okay, I undid cosine.
In the cafeteria.
Sorry about that. Okay, so in this case, what we're going to do is now we undid the cosine, and we're going to get pi over 60 times x, and then equals the quadrant 2 angle, pi minus. And again, when I undid that cosine, everybody, I'm left with pi over 60x, and so that equals the quadrant 3 angle, and that would be pi plus. Wonderful. Now, I think we can let it ride. So when all's said and done here, I'm going to get this piece right here, and just kind of looking at the time. Let's see how we can do with this. Everybody do pi minus this on your calculator, please. And then multiply by 60 and divide by pi.
Pancakes in the cafeteria.
Okay, so when I did this, I ended up getting 40 seconds. And same deal over here, everybody. When this came into being, I've got this piece, multiply by the 60, divide by pi. And again, please confirm as you do this stuff on your calculator, make sure you not only see how it works out, but that you're able to pull it off on your own. And I get 40 and 60 as a result. Wonderful. Now just real quick, and then kind of let you go with this piece. What I saw initially was this. Cosine ratio is -1/2. Well, I know when I do that in quadrant 2, that angle actually is 2 pi over 3. That's the one that has the cosine ratio of -1/2. And as a matter of fact, that's exactly what this is. And in quadrant 3, that angle actually happens to be 4 pi over 3. And that's exactly what this is, as a matter of fact, 4 pi over 3. So in reality, what you did there, everyone, was did pi over 60x equals that, and then pi over 60x equals that. And when you solved, of course, we got our 2. 40 seconds and 80 seconds. Okay. Wonderful. So some good practice with this piece. Looking pretty good there. Just you'll see some of this stuff with the unit circle, solving equations where, we do have our cosine ratio in this case right from the unit circle, so we would use that. Or, again, if it's not one of our good ratios from the unit circle, then we have this 3-step process. Reference angle, quadrants, solve. All right, so some good stuff here, a little 3-day set. You're going to be working on a partner challenge with your notes on this, do some application problems, and then also an individual quiz, kind of working more along the lines with the unit circle type stuff that we did on day 1, but also just some of maybe the easier approximation problems. So again, different types. Please ask questions as you get some practice on them. But in terms of the 2-part quiz, one with a partner and your notes on the applications, and then one independently there, and you'll just schedule with that with me when you're ready. Well, of course, thanks for listening, and let me know if you have some questions.